Am I audible? Hello, hello. Good evening, class. As you know, I am Mohit, and this is the assignment third class. Assignment third class of course Quantum Hole Effect, offered by NPTEL. 2025. Today is 16th August 25. And since this course is about the quantum Hole effect and its origin, understanding the Berry curvature, understanding how the momentum operator commutes in presence of the magnetic field. In today's class, I'll be covering commutation relation of momentum operator, of two-dimensional progress, momentum operators, in presence of magnetic field, then effect of spins on the Landau Venn diagram, the Landau energy diagram, then the what is Berry phase, how a electron when moving along a path acquire a phase and how it is different from that IH bar, IET by H bar, the time governed phase, how it is different from that, and how by interfering the two waves you can get these interfering signals, which tells you about more about the intrinsic property of the system. Like being in the Morse system, it tells you about what is the periodicity associated with the Morse and all those things. So, like for example, in the Aronow-Bohm effect, you see when you have two superconducting half rings and then you move the electrons along those rings and you do the interference pattern by passing the magnetic flux through threading through that area. So then there will be Berry phase and corrections between Berry phase and Berry curvature connections, and maybe lately, if time permits, the effect of electric field on the Landau spectrum. Yeah. So with all these, I'll start with the first problem and then we'll keep on going to solve the subsequent ones. Okay. So let me start by putting the first question. This is question number 1. It says that okay, consider a two-dimensional electron gas in which the velocity of the electrons is given by v is equals to x component and y component, because it's two gas carriers can't move in the z direction, and there is a uniform magnetic field, uniform perpendicular magnetic field what we call the BZ cap, and then we are free to choose any gas and find the commutation relation between Vx and Vy. What will be the value of Vx and Vy? So, mm, so this is nice. This concise and self-contained derivation, which we'll do, and I'll show you that this is case independent. So whatever value of A you choose in the case, essentially the results will be the same. And let's start it. So first I will this solution. The setup of the problem is like a charge particle is there of charge q, and it is moving in a vector potential A. So charge q is moving in vector potential A. Here q is equals to minus E in our case, vector potential A, which is a function of positions. So your momentum operator will be pi is equals to canonical momentum minus q A, right? And velocity operator we know, your momentum, your velocity will be Vx, for example, you are saying. So pi x by m, where m is the mass, effective mass basically. So I is x and y, because Vx and Vy two are there. And we know for electrons, for electron, q is equals to minus E. What this implies? This implies that pi is nothing but, okay, let me just write it. Pi is equals to P plus EA. Right? Now we assume that we have perpendicular magnetic field B is equals to Bz cap. So we know that B will be what? Curl of A. Right? So let me call this one as equation 1, equation 2, equation 3. Right? Now we'll have to compute commutation of pi x and pi y. So compute, because if we can compute computation of pi x pi y, then Vx Vy we can just replace by pi I by m for Vi. So we have to compute pi x and pi y, and we know from on the mechanical course, basic course, that Pj, whatever Pj you write, will be minus I h bar del by del j. Right? That's what it means. So if I take Pj and the commutation of it with the function which is position of r, for example, in our case it is vector potential A, then it will be given by minus I h bar del by del j. So I will write del by del j of f for any function, right? So now using this, I can write pi x pi y is equals to px minus qax and py minus qay. We know that px and py commutes, that's why they will go to 0, and only term which will survive will be, you can do this small mathematics part, and the things which will survive will be px ay and plus ax py, right? And if you follow the equation number 4, or let me say, if you follow equation number 4, using equation 4, you can rewrite it as pi x pi y is equals to minus q minus I h bar del x ay plus I h bar del y ax. And if you just do a bit of math and just rearrange the terms, what you will get will be dx ay minus ay minus del y ax. And if I ask you what it is, you will straightforward say that okay, let me look at the equation number 3. So it is nothing but I h bar q times what, curl, this is curl of A, right? And we know that from equation 3, curl of A is B, essentially I h bar QB. So therefore, commutation of pi x and pi y is I h bar QB. So commutation of Vx and Vy will be what? 1 by pi x by m and pi y by m, and this is 1 by m square pi x pi y. Let me call this equation number 5. Substituting 5, right? What you will get? Vx, commutation of Vx and Vy will be I h bar q b by m square. In our case, q is equals to minus e. One electron charge is there, right? And we know the electron charge is minus e. So minus I h bar eb by m square. And we know that eb by m is nothing but omega c. So minus I h bar omega c by m. This is essentially what the commutation relation of the velocities of Vx and Vy will be. They are non-zero in presence of magnetic field. See, if V is equals to 0, Vx and Vy commutes, else not. It means in presence of the magnetic field, the commutation between Vx and Vy breaks and it gives non-zero value. So the functions of basically the plane wave which was there for Vx and Vy, earlier it was commutating, right? But now in presence of the magnetic field, they won't commute with each other, and that's what you see here. There's intermixing and the states, so they don't commute. Yeah. So this is about the question number 1. Now let me go and head toward the question number 2. The question number 2 is goes like oh, you have these electronic charges in your system, right? And these electronic charges are there. You put them in the two-dimensional electron gas and turn on the magnetic field. What it does is generates these what so-called Landau levels. Now, all those derivation which I did in the previous class, was for the spin non-degenerate system. We did not talk about the spin, but we know the electron has two of these quantum numbers. One is spin up and another is spin down. And what will happen if you have that system and you turn on the magnetic field? How your Landau level spectrum will change? So this question is about that only. So the question is compute the Landau level spectrum for a spin non-degenerate, spin degenerate system placed in magnetic field, placed in large magnetic field. Okay, it can be large, it can be small, so the physics won't change. So, okay, let me start with the one which we have discussed in the first and the second lecture of our course, that Landau levels without spin. That's what something which I have derived already. So Landau levels without spin. So we have an electronic charge minus E or mass m and 2D mass electron gas moving in perpendicular magnetic field B. Right? Now the magnetic field is Bz cap, let's say, and my this two-dimensional electron gas system is in x and y direction confined. So this is my x and this is my y, and I apply a magnetic field which is Bz cap. This is something which we have derived, and we know that the energy levels, Landau level energy levels are En is equals to h bar omega c n plus half. Right? No. Where n is a quantum number, 0, 1, 2, it is an integer, belongs to integer. And omega c is nothing but Eb by m. It's the cyclotron frequency. And each Landau level is highly degenerate, that we have discussed, and proportional to the flux through the sample, that is Eb by h per state unit area. So the degeneration with the degeneracy 5 by 5 naught. 5 by 5 naught. Now we are including spins. So let me divide into parts. This is first part. Now I will go to the second part, which is I will include the spins, including spin. We know that whenever the spins are there in presence of the magnetic field, there is this Zeeman splitting is there, right? Zeeman splitting. So the electron spin couples to the magnetic field by the Zeeman interaction. The electron spin couples to the magnetic field via Zeeman interactions. What is Zeeman Hamiltonian? It is like minus Z mu B S dot D. S is quantum number, and D is the applied magnetic field, and H bar is the Planck constant. Mu B is what we call Bohr magneton. So here G is Landau factor. Mu B is E H bar by 2m and known as Bohr magneton. Spins is S is spin quantum number. Can be plus minus half, whether it is in the direction of the applied field or in the opposite direction, anti-aligned or aligned. And if you substitute these ones, your equation Hz will turn out to be minus plus minus half basically, for S is equals to plus minus half G mu B times B. Even if you substitute the value of mu B also, so it will be plus minus half G times G is 2 Landau factor, right? And G is 2, mu B is E h bar by 2m times B. And if you see it, it is nothing but E h bar B by 2m plus minus. And we know that what is this omega c EB by m. So this is essentially h bar omega c by 2. Compare it with equation number this is 1, this is 2, plus minus, right? So now the full Landau, how the full Landau level energy will go? Thus the full Landau level energy will be equation 1 plus equation 2. En, and that will be h bar omega c n plus half plus essentially plus minus h bar omega c by 2, if you see it. And for, because for electron, this is whatever the Landau factor I have written is for electrons. This is approximately 2. Okay. So this Zeeman splitting which you are seeing basically, so you had, if I ask you that okay, this h bar omega c is there, right? So it's plus minus. If I ask you En plus minus En minus, what is the difference of these two? You will directly say that okay, this is h bar omega c. And remember, this h bar omega c is also the energy difference between the two Landau levels. This implies that mean Zeeman splitting is equals to the cyclotron gap. So the spin branch of level n plus 1 coincides with the spin down branch of level n. Spin down branch of level n. Thus the spectrum forms a ladder of equally spaced sets, but each energy has contribution from different spin Landau index contribution. So this is in case of, for example, initially you had your Landau level, which was energy was like this, and you had it your levels, energy levels to be like this, right? The spins were not there, so n is equals to 0, n is equals to 1, n is equals to 2, n is equals to 3 for no spin considered, no spin, right? Now for spin, now for spin, non-degenerate system, Non-degenerate means the energy of the spin up and spin down is different. So what you will get, E. Okay. Now, since this is your n equal to 0 state was there, in which there will be a state of the down spin and there will be a state of up spin. So n is equal to 0 state, which was there like this. This will get divided into two. One will go here, another will go down here, equal to 0. So this will be n0 up spin. This will be n0 down spin. Similarly, n equal to 1 state was there here. This was n equal to 0. This is n equals to 1. But which is there if I compare it? So in this one also, there will be a state which will go down. So there will be another state of, I'll just draw the different color. It's exactly on top of this one, but will be of n is equals to 1, but spin down, and n is equals to 2, but spin up. N is equals to 1, but spin up, essentially. So what do you see here? So the essential gap between these levels always remains h bar omega c, and whatever, for example, this state, which is n is equals to 0, spin is up, and n is equals to 1, spin is down. They have the same energy. So it's hard to distinguish for the free electron gas, because there the effective mass is m cyclic electron mass. But when you have semiconductors, for example, gas system, right, gallium arsenide, there the effective mass is different. It's not the free electron mass. Their m star is different, so your Landau factor is also different. If your Landau factor is different, then your these levels will not lie on top of each other. Then they will be separate levels, individuals, and you can easily identify them by wearing the magnetic field. So for semiconductors, like for example gallium arsenide, electrons have effective mass m star. M star and an effective G factor. Right? And for gallium arsenide system, like for GaAs gallium arsenide, M star is what? 0.067 mass of electrons, and G is roughly 0.44, minus 0.44. What does this tell? This makes the Zeeman splitting much smaller than the cyclotron splitting. This makes Zeeman splitting much less than much smaller than the cyclotron splitting. Splitting. Tens of times smaller. Hence, Landau levels are nearly spin degenerate, and spin splitting. Hence, Landau levels are nearly spin degenerates, and spin splitting may only become visible at very high field. So that's about it. And so the consequence of it, as I discussed, each Landau level is split into two sub-levels, spin up and spin down. The degeneracy of each Landau level is half compared to the spin-less case when spin splitting is resolved. And the sequence of the filling Landau levels with electrons depend on the relative size of the Zeeman and the cyclotron energy. What I mean is, like, if Zeeman splitting is small, levels are almost spin degenerate and fill as n equal to 0 both spins, n equal to 1 both spins, etc. If Zeeman splitting is comparable or larger, the order of the filling alternate between the spin states. Example, first n equal to 0 upspin will fill, then n equal to 0 downspin, then n equal to 1 upspin, etc. The order can be like up or down depending on the direction of the magnetic field. And this affect the quantum hole plateaus. Additional plateaus may appear at the, and they do appear actually, at the odd integer filling factors when spin splitting is resolved. So this is something which is there. So in this question, we discussed what is the role of the spin splitting in the case of the uh, Landau levels. So till now we have addressed two questions in this assignment. Now I'll move on to more of a general question of the Berry phase, like how the Berry phase comes, what does the Berry phase mean, how it affects the quantities which we measure, how this phase basically affects all those things, and then we go on later connecting it to the conductance of the quantum Hall systems. So the question is, find the general form for the Berry phase for Hamiltonian H lambda, where lambda is a parameter that depends slowly on time. Yeah. So this is the question. Now we'll have to uh, find the general form of the Berry phase. And having said that, I'll start this part where we'll find out the general form of this Berry phase. Yeah. So this is an important topic that we need to review. That's what I think, before we can start the story of these quantum Hall effect, conductance quantization, fractional quantum Hall. All this, before that, this is something which need to be reviewed, and it is a subject of Berry phase, or more precisely the Berry holonomy. Basically, this is not a topic which is relevant just in the quantum Hall physics. By the way, it has application in many areas of the quantum mechanics and will arise over and over again in different fields of this lecture also. And if you do the quantum anomalous Hall effect, all those, the band related topological system. So moreover, it is a topic basically which perhaps capture the spirit of the quantum Hall effect better than any other. For the Berry phase is the right, and the Berry phase, this Berry phase is the simplest demonstration of how geometry and topology of uh, the band can emerge from the quantum mechanics. And I will show in this while solving this problem that indeed this is the heart of this quantum Hall effect, or what you think, this quantum mechanics also you can say, behind the two-dimensional electron gas in magnetic field. And I will describe the Berry phase arising for this general form of the Hamiltonian, which let me write at answer. Let me write the Hamiltonian general form. So let me give it. This has this lambda. Let me give it another knob also. The position and the lambda is the parameter which you tune. So A, whatever I have written, they are the degrees of freedom. Like move in X, Y, and Z direction. They are the degree of freedom, and these are the things that evolves dynamically. The things we want to solve basically in this problem. So they are typically things like the position or spin of the systems, right? So X, A are the degrees of freedom of the system. Can be position, yeah. It can be spin of particles also. Looks like there is some internet issue. Just yeah, particles also. And in in contrast, the other variable in contrast, the other variable which I am using, variable lambda I. This is the parameter of the. This is another parameter of this Hamiltonian, and these these lambdas are fixed with their values determined by some external apparatus that probably involves knob and dials like flashing lights and things which we do. We don't usually exhibit the dependence of h on these variables lambda i's. So these are the parameters Hamiltonian. And now comes the game. We pick some values for the parameter lambda and place the system in a specific energy eigenstate. Let's say the psi. So let's pick some value for the parameter lambda. Parameter lambda and place the system in a specific energy eigenstate psi, right? Uh, let's say this is the ground state. So that let's say this is the ground state of the system, right? And we assume this ground state is unique. We assume this ground state has to be unique actually. This ground state is unique. And this we will later relax this assumption also. And now uh, we'll slowly, we will slowly vary the parameter lambda, right? So the Hamiltonian changes, of course. So the ground state will also change. So the consequence of it will be the Hamiltonian will change if you vary the lambda, because Hamiltonian is a function of lambda and xa. Will change, and so does the ground state. That is psi lambda t, right? And we know in the quantum mechanics the adiabatic theorem. If you don't know, I will just state it. So it is a theorem in the quantum mechanics which states that if we place a system in a non-degenerate energy eigenstate, we place the system in non-degenerate energy eigenstate and vary parameters sufficiently slow, right? Then the system will cling to that energy eigenstate. It won't be excited to any higher or the lower states. So it won't be excited until unless there is no crossing. That's also important. It won't be excited to any higher or lower states. Lower states means the energy states basically. So uh, now how slow you have to be in changing the parameters, that depends on the energy gap between the states you are in, the like the nearest states which are there in a system. So the because when generally people say that we have to go slow, but how do you define the slow? So how slow you should vary the lambda? it ha- it has to be such that the so that changing the parameter lambda such that the changing the parameter lambda should not excite the level crossing. So the level crossing should not happen. For example, if you are having these energy states, for example, this is your ground energy, this is one energy state, this is another energy state, and let's say your energy states is like this, right? So you can take it along this path, but you should not excite it such that it transits to the other one, because after that you can't decouple them. Decoupling is hard. Even after that, these weights comes down, you won't be able to tell whether they are from the top level or they are from the bottom, because the intermixing has happened in the system. So those weights you can't decouple them. So that's why it's important that your level should not cross. Your system should remain in the same energy state. It should not cross that energy state to the another available state. So the idea is that uh, if you get level crossing when another states become degenerate, then all the bets which you have played they will be off. And when the states separate again, there is no simple way to tell like which linear combination of the states you now sit in. So anyway, level crossings are rare in the quantum mechanics. but they do happen. And in general, you have to tune three parameters to specific values in order to get two states to have the same energy. This, and whatever I'm saying, this follows by thinking about a general Hermitian 2 by 2 matrix, which can be viewed as the Hamiltonian for the two states of the interest. So the general Hermitian 2 by 2 matrix depends on four parameters, right? But its eigenvalue only coincide if it is proportional to the identity matrix. This means that three of those parameters have to be set to the zero, right? So the idea of the Berry phase arises in the following situation. We vary the parameter lambda, but ultimately we put them back to their starting values. This is something which you have to do. And this means that we trace out a closed path in the space of parameters. We will assume that this path did not go through a point with the level crossing. And the question after which remains is like, okay, now in which state we are now? So whatever I said, let me just try to write it if I can. So the idea of the Berry phase, right? And it arises in the following sense. So we vary the parameter lambda, vary the parameter lambda. We put them, we take it along a closed path, making sure there is no level crossing. There are no level crossings, right? And now the question is, in which state we are? We are now. So that's the question now, which is remaining. So the adiabatic theorem tells us most of the answer, right? If we start in the ground state, we also end up in the ground state. That's what the adiabatic theorem tells. So the only thing left uncertain is the phase of this new state. So you started with psi, and then you end up with, by picking some phase, e to the power I gamma. Gamma is the phase, and then psi, right? And we often think of the overall phase of the wave function as being unphysical. We think that, okay, this quantity is unphysical. Why do we think so? For example, if you are just taking psi, so it will be what, e to the power minus I gamma, and then psi, it will be like this, e to the power I gamma psi, and this will be what, psi. So essentially, a phase is not mattering, right? This is what we think generally. But see, here we are translating the carrier along a closed path. And that's the thing which will matter here will be the path difference. Generally, so let me just write. Generally, we often think of the overall phase as unphysical quantity. Overall phase of a wave function as being unphysical, right? But that's not the case here, right? Because this is a phase different. But here, that's not the case. It is actually a phase difference that matters. For example, we could have started with two states and take only one of them on this journey while leaving the others unchanged. And then after, later we can interfere these two states, and the phase e to the power I5 would have like these physical consequences which are measurable, like the Aronoff bomb effect. So the question then comes, okay, so then what is this e to the power I gamma? So what is this e to the power I gamma? So the answer to it is like there are actually two contributions. There are actually two contribution to gamma, right? The first is simply the dynamical phase, a dynamical phase. It's simply the phase which is acquired by any state when it translates in time, basically. And we know that it is e to the power minus I e t by h bar, where e is the eigenvalue of that wave, right? Even if the parameters are not changing, just with the time this phase evolves, right? And there is another uh, phase which is the Berry phase, right? So there are two phases. So gamma is composed of two phases. We know that dynamical phase does not matter, is unphysical quantity, because eventually when you take the expectation value, the phase disappears, right? Because all the states are evolving in the given time t. You can't stop the time essentially, but Berry phase depends on the path which you translate, and right, in which you are moving, and that you can control. So the dynamical phase you can't control. It's like it will evolve with time t, but the Berry phase you can, and something you can, then you can do the interference of these waves and can get the exciting physics. So now let's come to the computing the Berry phase. Computing the Berry phase. Right. So the wave function of the system of the system evolves through the time dependent Schrodinger equation. Right? That will be I h bar del psi by del t is h, and then which is a function of lambda of t, and then psi, right? I h bar del psi by del t equal to h psi. That's how you write it, right? And let me just label it like as equation number 1 in for this problem. Now for every choice of the parameter lambda, we introduce a ground state with some fixed choice of phase, right? And we call these reference state as n psi, n lambda. Let me call it n lambda. For every choice of parameter lambda, right, we introduce a ground state with some fixed choice of phase. right? And we call these states as, let's call these states as and lambda, right? So there is no canonical way to do this. We just make an arbitrary choice, right? We will soon see how this choice affects the final answer of our system. And we know, as we have seen in the adiabatic theorem, that the ground state psi t will be can be written as is ut and lambda of t, where ut is some time dependent phase basically, where ut is time dependent phase. Right? If you pick for example n lambda at t equal to 0, that is essentially what psi at t equal to 0, right? And then we'll have, that means u of t equal to 0 is essentially 1. Then our task is now to determine ut after we have taken lambda around the closed path and back to where we started. So our task is to determine ut, right, after we have taken lambda around the closed path and back to where we started. So there is always the dynamical contribution to the phase, as I discussed, like e to the power minus I, like the integration over time, and then e naught t by h bar. So dynamical phase will be e to the power minus I dt e naught by h bar, right? And where e naught is the ground state energy, ground state energy, and this note we are interesting here, right? So we will ignore it and we can simply select a, let's take e naught equal to 0. So this solves our complexity of the equation. So this dynamical phase now goes away, and what we have is this pure geometric phase, what we call the periphase. And this extra contribution now will be coming by this periphase. So let's plug this equation, equation 2 in equation 1, plug equation 2 in equation 1. So what does it say? I h bar, right? That's what it says. Del psi by del t is h is function of lambda t and then psi, right? So del by del t, whatever is there, let me call that as, that will be psi dot basically. And if you just combine it with substituting this, combining equation 1 and 2, you can write psi dot, don't mean the derivative, u dagger. Star means the dagger, the Hermitian conjugate of it, and n and dot. And we know, since we have taken e naught to be 0, this will be 0, right? And if that's 0, and then in that case, it's very evident that u star u dot will be minus n, right? And I can write this as del by del lambda I n lambda I dot. And it is useful to define the Berry connection now. Now let's define Berry connection. And the Berry connection is given as A lambda is equals to minus I n del by del lambda I n. So here n are basically the states, here states, energy states. And so therefore here u will read is to be minus A, this AI lambda dot I and then u, right? But you can easily solve it. It's essentially what d by dt is equals to minus I ai lambda I dot times u, and if you solve it, it will be a function of ut is equals to exponential minus I integral over ai lambda and lambda I dt. So our goal is here to compute the phase u, right? Whatever ut is there. So after we have taken a closed path C in parameter space, this is simply what e to the power I gamma is essentially exponential of minus I over a closed path C ai lambda. Ai is essentially the Berry, is actually Berry connection, and d lambda. So you can write lambda dot I to be d lambda by dt, and dt cancels, and that only leaves the these lambda i's, and this is the Berry phase. This is the Berry phase. And point to note here is that it does not depend on time, and that's the advantage. It does not depend on time taken to time of what time taken to change the parameters, right? However, it they do depend on the path taken through the parameter space, this closed path C which you are seeing. It do depend on the time taken to change the time taken. It do depend on the path taken through the parameter space. Yeah, and that's how we relate. If there is a Hamiltonian, which is a function of lambda, you vary the lambda, and then by you define your energy states to be like from the okay you let me go at the very beginning start. So you have your Hamiltonian H, in which xa is your degrees of freedom, and lambda I is the parameter which you can tune the knob. For example, it can be magnetic field. Generally it is the magnetic field in the interference pattern of these quantum Hall states, edges, all those things. And like being in the Aronoff bomb also, it's the magnetic field. So one of the parameters can be like magnetic field. Similarly, you can choose the other parameters, but you'll have to choose it such that the system moves adiabatically. Adiabatically means your edge, whatever your state is there of the system, that should not do the level crossing with another next available or the below available energy state. So it should be isolated so that its weight doesn't get transferred to the other layer. And because if they do, then it's whatever you are doing, the information is lost, because now those two linear combinations are there and you can't separate them. That's what the quantum mechanics says. Now, since you are in energy eigenstate E, you evolve over the time, you will always be in that energy eigenstate. That's what the adiabatic theorem guarantees if you don't cross. And then you have, okay, whenever a wave function moves in space, it picks up a phase. So there are two types of phases it picks up. One is the dynamical phase, that's the time dependent phase essentially, which every system picks over the time. Its value is given at e to the power I e t by h bar, and uh, uh, that is unphysical basically. You can't measure that phase because everything is evolving with time t, and there you can't make them one thing stop in time and other thing move. If you can do it, then you can of course do the interference patterns of these states also. But there is another phase which depends on the path you take. For example, this lambda parameter basically which I'm talking about. So you tune your carrier to move along a closed path, come back to the same position, and that will pick up a phase which will be having a physical meaning, and that's what is known as the Berry phase. And that you get by you choose your energy eigenstate wave function to be site equals to ut and lambda t. Ut is something which depends on the time dependent phase, and if ut equal to 0 will be 1, and our task then becomes to determine ut after we have taken lambda around the closed path. You take your e naught ground state energy to be 0 so that the at least the dynamical part goes away, the time dependent part basically. And then you substitute equation 2 in 1, you solve this equation just simply, and what you get is the Berry connection form, which is minus I uh, expectation value of d by d lambda of the eigenstate n, and you get also the Berry phase, which is the integral of your Berry connection over the path, closed path basically. And that's what the Berry phase is. Berry phase mean, and then this Berry phase is eventually connected to your Berry curvature, and your Berry curvature gets connected to your conductance quantization sigma xy, and that's how the role of your Berry phase will be. If this is clear to you, then we can move on to the next question also. And the next question will be, what is the role of disorders in quantum Hall effect? Question: role of disorders in quantum Hall effect. So in this section, we will discuss about what is the role of because whatever system you have, the two-dimensional quantum gas, it will be having some disorders, right? And what will be the impact of the disorders on your quantum Hall effect? So this section will cover that thing. So we have in the very first class all the previous classes also, we have discussed like the observation of your conductivity quantization. Basically, your conductivity is quantized in units of h e square by h, right? Sigma is nu square by h, and these are your news, nu equal to 1, 2, 3, 4, like this, right? And since now you have these conductors quantizations and you have these good plateaus, it turns out that it is actually the existence of the disorder which make these plateau look nice, flat, and it will be, I'll be discussing it. And so uh, plateaus owe their existence to one further bit of physics, and that one further bit of physics is nothing but a disorder. Disorder makes these plateau flat. So this arises because experimental samples are inherently dirty. They contain impurities which can be modeled by adding a random potential Vx, right? So uh, samples are inherently dirty. What do you mean by dirty? Dirty means to the dirty clothes? No, it's like you have your system. Maybe ideally it should be a perfect crystal, but there can be some impurity sitting there which can deflect the path of the electron. So that will also act like impurity, right? Some foreign particles, charged particles there, or foreign atoms sitting there, tape residue while fabrication, maybe some PM, organic solvent residue. All these comes as impurity because they act like a local scatterers, and when electron moves, they scatter those electrons, and that's why we call them the impurity. And these impurities can be modeled by adding a random potential Vx. Okay, and this is something we can add to the Hamiltonian to H. That means Hamiltonian. And as I will explain, this random potential is ultimately reasonable for this plateau what we observe in the quantum Hall effect. And there is a wonderful irony in this. The glorious precision with which these integer fillings are measured is due to the dirty, creepy physics of the impurity. Basically, these dirt would not have been there. You would not have been able to. That means the impurity, basically. And I had already defined the impurity. And if they would not have been there, we would not have been able to measure those precisely flat uh, uh, quantum Hall effect. So to see how this works, let's think about what disorder will likely do to the system, right? So our first expectation is that it will split the degenerate eigenstate that make up a Landau level, and this follows on general ground from quantum perturbation theory. Any generic perturbation which does not preserve symmetry will break degeneracy, right? And we will further ask that the strength of disorder is small relative to the splitting of the Landau levels. So we will in our case we assume, because if you are seeing this plateau, in that case v is less than h bar omega b or omega c, whatever you call a cyclotron frequency omega c. And in practice this means that the sample which exhibit the quantum Hall effectively actually have to be very clean. So the quantum Hall sample has to be clean. If it is not clean, has to be clean. If it's not clean, then in that case your V impurity will be too much compared to your H bar omega C, and then uh, that will basically smear out all your Landau levels. You won't be able to see the physics. So we need disorder, but not too much disorder. Mean we need, of course, we need disorder, but not too much. So the energy spectrum in the presence of this weak disorder is expected to change the quantized Landau levels from the familiar picture in the left. Okay, I will draw here this here energy versus you basically density of state. So DOS energy, you have these states, right? Landau level states. It's separated by h bar omega c without disorder, right? And if I do the same on the right, so I'll just copy it. Yeah, so we'll have to copy it, paste it, and now I will draw for the with disorders. So with disorder, they will become like this. Instead of very pinpointy flat like Dirac like, they become more of like the Gaussian or that kind of thing. So it is disorder with disorder, right? So there is a second effect of disorder. It turns many of the quantum states from extended to the localized. So it turns uh, many of the quantum states from extended to localized. And here is an extended state is spread throughout the whole system, right? uh, that's what we mean the extended state, a state which is spread well throughout the whole system. And in contrast, a localized state is restricted to lie in some region of space. It's restricted, it's not throughout the whole system. So yeah. Let me just write the extended state and the localized state definition also, so that it means the state that is spread throughout the whole system, the whole system, right? And in contrast, the localized state is a state which is restricted to lie in some region of space, right? So we can easily see the existence of these localized state in a semi-classical picture, which holds if the potential in addition to obeying this equation which I have written, V less than h bar omega c, varies appreciably on distance scales much greater than the magnetic length. So your delta V, the change in your potential gradient of your V has to be less than h bar omega b by lb. So it should not be abruptly, right? It should be smooth kind of thing. So with this assumption, the cyclotron orbit of an electron will take place in the region of essentially constant potential, right? With this assumption, the cyclotron, because when you place the electron in the magnetic field, what will they do? They do the cyclotron motion, right? Cyclotron orbit of an electron take place in a region of essentially constant potential, right? And the center of the orbit X will then drift along the equipotential surfaces. And to see this, we can introduce these quantum operators, which will show the center of these orbits. So let me call them X and Y. So your X will be X operator, that will show the thing will be pi y by m omega p, and your Y is essentially Y plus pi x by m omega p. Your pi y and pi x are the momentum, mechanical momentum. Your pi are the mechanical momentum, right? Recall that in contrast to this canonical momentum p, pi is gauge invariant, and the time evolution of these operators will be given by time evolution of these operators will be what? I h bar x dot is equals to x h plus v equals to xv, and xy del v by del y, and that will be essentially I lb square del v by del y. Similarly, I h bar y dot will be minus I lb square del v by del x. Here we have used the fact that in absence of the potential, uh, x and h commute, y and h commute. Here we have assumed in absence of potential, x h equals to y h equals to 0, and together this we will get the commutation relation of x and y to be I times lb square. Lb is magnetic length. This says that the center of the mass drifts in direction x dot y dot, which is perpendicular to delta v. In other words, the motion is along equipotential. So this says that the center of mass drifts in a direction x dot y dot, which is perpendicular to delta v. In other words, the motion is along equipotential. And uh, now we can consider that this means the random potential with various peaks and troughs. We basically uh, the, will be having the local maxima and the local minima, because and these particles will move anti-clockwise around the maxima and will move the clockwise around the minima. In both the cases, the particles are trapped close to the extrema, right? And they cannot move throughout the sample. In fact, equipotential which stretches from one side of a sample to another are relatively rare. So one place that they are guaranteed to exist is on the edge of the sample, and the upshot of this is that the state at the far edge of the band, either of high or something, like I will draw here. You had this figure, right? You had this figure. The dense shift state will look something like this, with these black one being the extended state, and this the broadening which is coming to these ones, the red ones, they are the localized states. So that's these are the extended and the localized states, and because of these only, since these available states are there, so in the carrier density you can move, but you won't be going to the next Landau level. In that case, your conductance is essentially through the edges, which is by the extended state, and these localized states just help you ping the your Fermi energy. So over a range of the carrier density, you do see those plateaus, nice plateaus, and that's how these impurity in the system. Impurity means these localized potentials help you essentially observe these nice plateaus. So that's what it is, and uh, yeah. So this problem is about this only, that how your disorder helps you observe your quantum Hall effect in a system. Uh, if the time permit, I can take one more question also, and yeah, let's do it. Let's do it. So next question is, what will happen if you put a two-dimensional electron gas in perpendicular magnetic field, and along with that in the electric field in the x direction? How discuss, basically let's say the discuss two dag placed in a perpendicular magnetic field Bz cap, and effective electric field in x direction, electric field E x direction, right? So let's discuss this one. So the conventional quantum hole which we have discussed in our class, that is around like you place your two-dimensional electron gas in presence of your magnetic field, perpendicular magnetic field, and then you see how it evolves. But when you keep your electronic charge, a two-dimensional electron gas, in perpendicular magnetic field and the electric field, then there is something funny happens, and so the potential, electrical potential due to this electric field, due to uh, E is what, phi is equals to minus E times x, right? And if this is the potential, in the potential energy you multiply it with the electronic charge minus E, so that will be E, capital E times x. Now you can write a total Hamiltonian to be p 1 by 2m, then px square, and then py plus ebx. So here I chose the Landau, this case to be b times x, because my magnetic field is in the z direction. So I can choose. This we have discussed also. Like you can choose any of the case, and that will give you the essentially the same physical results. The gauge invariancy theorem tells you that, and so that's what it is. So this is the Hamiltonian. Now we can assign the answers to it like we did it for the two-dimensional electron gas in magnetic field, and we will simply have to complete the square to again write the Hamiltonian like we wrote for the harmonic oscillator, right? And the states then can be related to what we have done previously. So I'll just follow the results from the, you can follow those lectures, and what you will find that your wave function can be written as psi n k. N is your Landau number, and k is your basically wave vector, and me by eb square. So center is shifted essentially,
when you place it in the presence of the magnetic field, your center essentially gets shifted. So x is now shifted to x plus me by eb square, and the energies then will be given by, and the energies will be given by what enk will be h bar omega b n plus half minus e k lb square plus e by m omega b square. This you can solve and easily get from the quantum mechanics equation if you solve those equations. So these will be their energy eigenvalues, and this is interesting. This form is interesting. This form is interesting. Why? So the degeneracy each Landau now has been lifted, right? And the energy in each level now depends linearly on K. Earlier, all those K were having the same energy, right? Now it depends on the K. And as it can be seen in the figure also, now earlier it used to be flat, right? Now your Landau spectrum will be something like this. So this n equal to 0, 1, 2, 3, 4, and this x is your k. So the uh, degeneracy of each allele is lifted, right? And because degeneracy, the energy is each, the energy in each level now depends on k essentially. And with this one, because the energy now depends on the momentum, it means that the states now drift in the y direction. So it means that states now drifts in y direction. And what is this drift velocity? Vy will be 1 by h bar del E electric nk del E by del k. E is energy, and that will be minus E by h bar E times lb square and minus E by b. So for E equal to 0, Vy is 0, no drifting, but E, for finite E, there will be drifting. This result is one of the surprising joys of classical physics. If you put an electric field E perpendicular to a magnetic field B, then the cyclotron objects of the electron drifts, but they don't drift in the direction of the electric field. Instead, they start drifting in the direction E cross B, which is both perpendicular to magnetic field and the electric field. And here is we see the quantum version of this statement, that why the electrons in the presence of the magnetic field they drift in the vy direction, right? We say that electrons have this force v cross b. So this is essentially that force which you are seeing here, which is derived quantum mechanically. So uh, this is the quantum mechanical version of Lorentz force, right? And the fact that the particles are now moving also provide a natural interpretation of the energy. A wave packet with momentum k is now localized at position x is equals to minus k lb square minus this one, right? And minus ee by m omega square. This part which you are seeing here, this is now at localized, and the middle term above can be thought of as the potential energy of the wave packet. So the final term can be thought of as the kinetic energy of the particle in the y direction, that is half mvy square, this part. So this part can be thought at like uh, half m vy square. This is essentially the potential energy and this is essentially the harmonic oscillator energy. So this is how your system can be thought. And with this one, we saw that okay, if you put a two-dimensional electron gas in a magnetic field and electric field, but you see the Landau level degeneracy, which was infinitely degenerate, that degeneracy gets lifted. One thing. The other thing, what you observed is we saw that Vy now is non-zero, which was earlier zero for E equal to zero, but for Vy v is like minus E by V, and it tells us the fundamental explanation of the Lorentz force, that why electron drifts in presence of electric and magnetic field. This is something which we also discussed in this class. If you have any question, answer or suggestion, you can ask me in the comment section. I'll be happy to address your concern. I'll wait for 2 minutes to take your question if there are any, and after that we'll conclude the class.